Hi everybody, I'm David, a PhD student at ASL working with tiltwing UAVs. In this case study, I'd like to give you some insights on how we model and control this kind of aircraft and what the related challenges are. I'd like to start with a brief introduction on tiltwings in general and why they are interesting. Then I would like to say a few words on the operational principle of such a tiltwing UAV before moving on to the core part, which is on one side our approach in modeling this platform for the purpose of control, but then also the controllers itself that are currently implemented on the tilt wing, which is the attitude controller on a low level and the cruise or velocity controller on a high level. So let's start with some zoology. As the name already tells, the tilt wing is a converted plane which tilts the wing together with the propulsion between an upright position for rotary wing hover flight and a horizontal position for fixed wing cruise flight. In between, we speak of the transition phase, and there the lift is shared between the propeller and the wing. The operation in the transition phase is somewhat a blend between helicopter and fixed wing. Now, the advantage of such a platform, as with almost every other hybrid platform design, is the combination of the flexibility that we get in rotary wing hover flight with the endurance, speed, and range that we get from standard fixed wing cruise flight. The idea of tilt wings is not particularly new. First examples date back 60 years ago. And although proven as a concept, tilt wings were never put into regular manned operation, however, and then not really further pursued. Only now, interest in tilt wings is sparked again for application with UAVs, but then also within the wealth of concepts showing up recently for urban aerial transportation, such as, for example, air taxis. What you see here is the Airbus Vahana or the Dufour Aero 2 from the Swiss startup Dufour Aerospace. And they both aim to become tilt wings for manned transportation. So maybe in a few years, we see some of these platforms actually transporting people again, which would be cool. Now, like with every design, there are particular pros and cons for a tilt wing. Comparing with a tail sitter, for example, and one advantage is that the fuselage remains horizontal most of the time, most of the time, apart from pitching. And this is beneficial if we are, for example, transporting people, but also depending on the payload that one might have, this is an advantage. Furthermore, the standard aircraft tail of a tilt wing gives it additional control authority when comparing with a tail sitter, which doesn't have this additional tail. Compared to a tilt rotor, a tilt wing features wing-aligned prop wash, so lift is generated earlier on in the transition, and overall, the forced flow over the wing gives it a somewhat more benign stall behavior. There are disadvantages, however, as well. Most importantly, a tilt wing is pretty susceptible to wind and hover due to the large area exposed by the wing and potentially facing into the wind. Then also, for the same reason, it has high air drag and hover, and in the end, the wing tilt mechanism itself might be considered too complicated. But this depends a bit on the application for sure. So what you see here is the tiltwing UAV that we're currently using at the lab. It's a standard RC aircraft that you can buy like this off the shelf. It's modeled after the Canadian CL-84, which flew in the 60s, and we refurbished this platform with Pixhawk flight controller hardware running the PX4 firmware on it, which we modified for our own purposes. And we're using this platform to test different control algorithms and our modeling approaches, basically. So before going into more detail on the modeling approach that we choose and how we're controlling this platform, let's have a look at the basic operating principles and the controls that we have available. So of course, there's the wing, which is able to tilt. Then we have the main propellers, which are mounted to the wing, and they generate most of the lift in hover flight. Furthermore, we feature a propeller in the tail, which is required for pitching in hover, and it's also able to tilt around the x-axis in order to actuate the yaw in hover. So overall, in hover, we fly this platform like a standard tricopter. Furthermore, we have the ailerons, the elevator, and the rudder, which sum up to the standard fixed-wing controls that we use in cruise flight. Now, with this combination of actuators, we realized that the platform is over-actuated for the task of attitude control. So for example, in hover, if we want to yaw, we can do this in two ways. We can either use the tilting tail prop, so the default standard tricopter way, or we can also deflect the ailerons, which are partly located in the slipstream in order to deflect the slipstream and thus generate a yaw torque. In cruise, there are also two ways to yaw. We can either use differential thrust on the propellers or use the standard way. Same for pitch, you can either use the elevator and or the tail prop. So with these combinations or multiple actuators for the same task, we have increased control authority in general, but we can also consider this as a set of redundant actuators, which in case one of them fails, we would still have a backup, which is also something nice to have here. Okay, so this would be basic operating principle of the tilt wing. Then, in order to control it, we first need to have a model, and when doing so, we face similar challenges as we've been introduced to in the case study on the wing trap tail sitter. So first, there's the wide range and angle of attacks that the airfoil and the tilt wing faces. So we really need to make sure that we capture the full 100 or 360 degrees range and angle of attacks. So we model the lift and drag curves qualitatively as you see it here in the plot on the bottom right. Then we have the interaction between the propeller and the wing. So for those segments of the wing which are located behind the propeller, we need to consider the propeller slipstream. And what we're doing there is a simple superposition of the free stream velocity VA with the slipstream that we calculate based on standard disk actuator theory. Then we can calculate the local angle of attack and adjust the lift and drag accordingly. Furthermore, and this is a bit different from a tail sitter, we have the standard aircraft tail, and there is especially the horizontal stabilizer, which is affected by the wing in front of it. So this is on one side the downwash of the wing, but then also in transition we have for sure turbulent flow, which acts on the horizontal stabilizer, and this is really pretty hard to model. In our current approach, we just assume that the horizontal tail is just in the plain free stream, but this is likely not true in reality. Overall, the question that we are asking here then is like, what is actually necessary for control? So currently we're doing somewhat well with a modular component buildup. So we partition the aircraft into multiple segments, and then we sum the forces and torques of each individual airfoil segments, which generate lift and drag according to the curve you see on the right. The separate propeller units, which also mostly generate the thrust and drag, but then also the slipstream, which in turn affects the airfoil segments, and then the fuselage, which is mainly generating drag. So we partition the UAV into these different components and do calculations on them separately, put everything back together, and this determines then our dynamics. So to illustrate this, what you see here is a simulation that we have. On the left-hand side, you see a very crude rendering of the tilt wing in its whirl. And on the right-hand side, you see an illustration of the acting forces and the slipstreams varying over time and depicted as colored vectors. So as I play this here, you see here on the right, as we increase throttle, thrust increases as well on the prop. And then in blue here on the wing, we have the locally calculated slipstream. And then here the long green vectors are the lift generated on that particular segment. You see those vectors are pretty much longer than the one on the tip of the wing, where we only have a free stream and a different angle of attacks and pretty much lower dynamic pressure. So this is why here the lift was so small. So this should somewhat illustrate this component-based approach here. You see the wing has 8 different segments, 2 on each side are subject to the slipstream of the propellers. And on the tail, we too have these segments and so on. Yeah, so okay, with the model at hand then, the next step that we do is try and identify the parameters that we have on them in order to match the behavior of the real system as closely as possible. So this amounts to a gray box system identification process here. What you see in these plots is on the top 2 plots in blue, you see the measured linear acceleration in X and Z direction during a flight, which includes both hover phases here in the beginning, and transition in the middle, and cruise flight in the end. In red, you see the fit of our predicted model, or predicted acceleration, which is predicted by our model, based on the current state, and we chose the parameter such, or fitted the parameter such, that these 2 signals match as closely as possible. And you see that basically the parameter model we're using has good descriptive power, so we're fairly well in fitting this data here. The downside is that it's over-parameterized, so there are a subset of parameters or different combination of parameters which yield the same input-output behavior. And within this basically null space of the parameters, we are free to choose different values. So there's also manual tweaking involved here. We need to make somewhat sure that they're, or where we make sure that they're somewhat close to physically reasonable values. And yet there are some gaps which still need to be filled. So even though it's quite descriptive, it can still not match the full reality. So reality is still a bit more complex. And so in the future, if we decide that this is required to increase complexity further, we can also use model-free components, such as like universal function approximators here, if we see that certain effects still need to be modeled for control. To illustrate one of these effects that we have in reality, but which is not modeled in our model, let's have a look at the wing here during transition from cruise to hover and then back again. And what I would like you to look at is, like, first of all, we have these two segments here in red, which are only subject to the free stream, and then we have the blue segment, which is located behind the propeller, and thus, in addition to the free stream, also sees the slipstream of the propeller. Now our model would assume somewhat uniform slipstream for this entire area here. But as we will see in a second, we can actually partition somewhat the behavior into the left and right hand side. So we'll see these tufts, so these strings that we mounted here on the propeller, they're used to indicate whether the flow is attached or not, or somewhat laminar or turbulent. You'll see that the flow behavior is different on the left and the right hand side as we're going through a transition. So let me play this video here. We're in cruise, now we're starting to tilt the wing up. You will see that here on the right hand side, the tufts start to dance around quite wildly, indicating that the flow is detached and very turbulent. And then again, the left-hand side was somewhat better attached throughout the transition. Same is or can be observed when you're going from hover to cruise again. And the reason for this different behavior on the left and right-hand side is that the propeller slipstream also has a swirl component, which is, for example, not modeled in our current approach. And it, in effect, causes that on the left-hand side, we have a lower angle of attack than on the right-hand side. Thus, the right-hand side showed this more pronounced stall behavior because it overall has higher angle of attacks, maybe even higher than the free stream components here. So this just as an example of how the reality is actually more complex than what we're modeling. But I mean, I guess you would have expected this anyway. For the purpose of control, however, the model is somewhat okay so far. So we're in a good position to start implementing controllers. For one, because we want to prevent this from happening. So the platform is inherently unstable. So we need to make sure that it flies stably and don't crash. But overall, we would also like to have well-performing operation and eventually enable applications for tilt wings in general. So what you see here is the currently used control structure. It features a similar hierarchical architecture as you've been introduced to in the fixed wing lecture. So we have a high level and a low level. The high level generally is tasked with things such as velocity control up to trajectory generation and guidance, whereas the low level is mainly tasked with attitude and rate control. So basically kind of the stabilization of the platform as well. Currently on the tilt wing, we have the low level implemented as well as the velocity control. And so in the following steps, I would like to focus a bit more on those two elements. So for the low level, you see it features somewhat cascaded structure as well. I will explain this in a second. Just for now, focus on the input. So we have the desired attitude and the current attitude, and we calculate the desired control surface deflections and corrective thrusts. Note that we have here, or speak of corrective thrust, because externally we provide a average thrust or throttle setting for the propellers, and so this loop here just corrects those to actuate the attitude. And also similarly, wing tilt is provided externally or by a higher level loop, basically. Now all this is implemented on, so the controller together with the state estimation runs on the Pixel flight controller in a somewhat customized PX4 firmware. Okay, so let's go through this lower level control now step by step. The first part takes the desired attitude and current attitude and basically calculates the desired angular acceleration. This is a two-step process. So first a P controller, then a PID. So again, somewhat cascaded here. This scheme is completely model independent, so it's really just geometric basically and defines the reference dynamics that we would like to follow with our platform. With the desired angular acceleration at hand, we can then use dynamic inversion, which in this case is basically just solving rigid body rotational dynamics for the torque, so pretty simple. And we calculate the desired net control torque, which would achieve this angular acceleration. Note that this is the first model-based step because here we need an estimate of our moment of inertia of the platform. So with this control torque at hand, we can move on and then use our aerodynamic model to figure out what the control surface deflections need to be and what the throttle settings need to be. This is done in a two-step approach. So first, we ask basically our aerodynamic model, which for example also uses current airspeed and so on. What is the current aerodynamic torque, or what does the model tells us that the current aerodynamic torque is? We then compare this with the desired net torque and get a residual torque that we'd like to actuate with our control surfaces. We then move on over to the allocation where we try to figure this out. And recall here that the platform is over-actuated for the task of attitude control. So there are multiple ways we can use the control surfaces and combine with the throttle settings. And what we're using here is a heuristic called chaining of actuators to deal with this over-actuation and get somewhat the prioritization of actuators. So I'll explain this right here in more detail. So we have this desired or residual torque that we'd like to actuate from before. So this is the delta that we still need to add on what we already have in order to achieve the desired torque. So for example, for the yaw axis, we have small n, which is the desired yaw torque. And then we go to the rudder and first of all try to achieve as much as possible of this torque with just the rudder. Now it might be that this torque is just generally too high, or the rudder is not effective because airspeed might be low, for example, in hover. So it's well possible that we saturate this rudder or this particular actuator and then are left over with a residual torque. This is then passed on to the next actuator group. Somewhat similar with the elevator, we use that one first to allocate pitch, and if it's not sufficient, then we pass on the residual to the later actuator groups. Note that the wing is responsible for both, or the actuators on the wing are both responsible for roll and yaw torque generation, so we allocate them jointly here. And in any case, in the end, we might still end up with some residual torque, so having a full saturation of, at least with using the scheme. And so what we would need to do in this case is detune basically the attitude controller and make this a bit less aggressive. So saturation is something that we want generally to avoid because it might skew basically the direction of the moment that we actuate and the behavior might be somewhat off. Now in general, I said already, it's a heuristic approach here. Depending on the order that we choose to allocate these different actuators, we might waste some control authority. We also deliberately saturate single actuators. So this might sometimes not be desired. Ideally, what one would do is formulate the nonlinear constraint optimization where we try to minimize this error here, basically achieve, so not minimizing, this error, but achieve a control torque which is as close as possible as to this desired control torque, while prioritizing the use of some actuators over the others and constrained because those are having all their own constraints, of course. But this is typically computationally too expensive, so we rely on this more simple, although not optimal, heuristic of chaining the actuators. So now let's have a look at what this looks in action. Here doing a back transition where the attitude controller is tasked to keep somewhat a level attitude, as you see here. And on the right-hand side in the plot, you see the control signals sent to the actuators, whereas in cruise, for example, the violet signal here, the elevator is somewhat in a neutral position, and then as we start to tilt the wing up, we generate a negative pitch torque, which we need to compensate with the elevator. So we start deflecting more and more and more until it saturates, and this is where the tail prop starts to rev up. So this is illustrates nicely this chaining of actuators here. Also then in the end, once the airspeed is really low, we also put the elevator back to neutral position, and here have some kind of a additional kind of tweak that we don't end up with a very twitchy elevator here, because again, it's first allocated first, and if we don't have any or don't prevent this actively, it will just always saturate here because it's so ineffective basically. And so we have an additional kind of smoothing here that if it's really not effective at all, that we just set it back to 0. Okay, so now with an attitude controller at hand, we can already have quite some fun with this platform and flying it around. But then to achieve really automatic or even autonomous missions or operation, we for sure need the high level. So far, we have the velocity controller implemented, and we'd like to share some more light or share some insights on that one as well here. So the idea is that we give a desired airspeed here, just longitudinal airspeed, so vertical and horizontal velocity, and we calculate a wing tilt, the mean throttle setting, and the desired attitude to achieve this airspeed. Note that these are the necessary and sufficient set of actuators or states that we need to control airspeed. So in hover, for example, we use the throttle for vertical velocity control and the pitch somewhat for horizontal velocity control, and vice versa in cruise. So one of the main challenges with this cruise controller is the strong nonlinear variation of the pitch dynamics, which includes on a lower or kind of as a sub problem, the steady state actuation of the platform. So what we can do is ask ourselves, given or assume that we're already at the desired airspeed, what would the input look like in order to stay there? So the steady state input given at desired airspeed. Then we can calculate the trim maps that you see here, and then use those kind of as a lookup table for feed-forward control later on. Now, it's important to realize here that also for this task of cruise control, the platform is overactuated. So for example, if you want to have 0-0 airspeed, then you can do this multiple ways. You can do it in standard hover configuration, but you can also have the fuselage at 90-degree pitch and the wing in cruise configuration. So there we need to include additional objectives besides just reaching a steady state to have a unique solution. And yeah, generally what you see here, like in hover, the wing is at 90 degrees, and then as we go to cruise, we put it down to 0 degrees. The throttle here, interestingly to see, is so the entire colored area determines the flight envelope of the aircraft, and here that one is basically bounded by the maximum throttle that we can achieve. So we cannot steadily keep like a velocity above, say, what is this, 26 meters per second in level cruise flight. This is just not possible. And for the pitch, what you see here is kind of the logic that we have, that we align pitch with the flight path angle. So this is a polar plot, actually. I should have mentioned this. So airspeed equals radius, and flight path angle equals the radius here. So for the pitch, we align the pitch angle with the flight path angle, the faster we go, whereas in hover, it's somewhat level all the time, no matter whether you're flying up or down. This is kind of, as a passenger, you would probably feel more comfortable to stay level at slow flight, but then more behave like a fixed wing in faster flights. So these trim maps, basically, this trim analysis forms a core for the cruise controller, which is shown here. So you will see that there are two paths in here. First, we have the feed-forward path, where we take the desired velocity commanded by the pilot, user, or even another higher level. And then we basically go into trim map and look up the corresponding trim pitch, wing tilt, and throttle settings. Note that we should, however, not choose a trim value for a velocity which is too far away from our current velocity, because then this might just be way too off of as a feed-forward turn basic for our current state. So what we do is constrain the lookup in the trim map based on our current velocity. So we don't just go to the desired velocity, but rather bound this somewhat close to the current velocity, so then also the trims are somewhat right for our current state, but go in the right direction. Note, however, one important part is that these trim inputs, they match a certain airspeed and then define a steady state. But a steady state by itself is not guaranteed, or not generally also a stable steady state. So if we are in a steady state, having these inputs and then are perturbed, it might not be guaranteed that we're actually going back to our velocity. So these points don't need to be attractive. So for that reason, but then also for disturbance attenuation, and because we for sure make errors here in the first place, we also need to have a feedback loop, which is the second path here, which is pretty simple. So first we take the velocity error and with a PID get a desired linear acceleration, relate this to a desired force, which then in a control allocation step is related to corrective pitch and corrective throttle, basically these deltas, which we add to the trim values. And we calculate this by using a control Jacobian here. So it tells us what or how does the force change upon a change of the pitch angle or the throttle setting. And then we figure out what these delta or this U needs to be. So J times U should equal this corrective force here. That helps us to accelerate from one to another velocity set point or helps to attenuate disturbances, etc. Again, if you have a look at what this looks like in action here, again, outboard view and inboard or onboard view. And you see here how we're ramping up and down or having these steps in the desired vertical velocity, and then we've tried to manage following this quite well. Also note how the wing always adjusts its position, and this is basically the lookup that we obtain from the trim map, so the wing is only feed forward controlled here because its dynamics are too unpredictable, but basically adapts itself in a somewhat optimal way, the way we defined it in our trim optimization. It adapts to the airspeed, which is commanded right now. Also note that in this case, only the vertical velocity was feedback controlled, the horizontal one, which was just feed forward. It actually turned out that this controller here is quite difficult to tune, mainly because with this allocation, we neglect the dynamics of the pitch and the throttles, or the thrusts, basically, which might be somewhat borderline in that case, so resulting in a undesirable control behavior. So it was easier to just control one of the two variables and let the other one be open loop, which then also motivated this approach here where we weight both of them in a regularized least squares approach. But in order to actually take these different dynamics into account, and especially also the dynamic of the wing, which was neglected in the first place already here, we're currently looking into using a model predictive controller instead, which knows about the different dynamics of the pitch of our thrust and the wing, and then therefore can dynamic allocate these different quantities so that they match together with their dynamics match up well. First results are also somewhat promising already. So we achieve simultaneous tracking of both horizontal and vertical velocity. And so we're developing this further at the moment. Okay, so with this, I'm almost at the end here. I'd briefly like to mention that, or give a bit of broader context of our research on tilt wings. So I already mentioned D4 Aerospace. It's a Swiss startup which works on tilt wings for manned transportation. They currently have a quite big UAV already, and we're collaborating with them to share experience on control, but then also get somewhat an understanding of how model translate between smaller and bigger platforms, and whether the model that we use or that we just presented here, whether this is general enough to be applicable to platforms of different sizes, which would be interesting also from a research perspective on how to model hybrid UAVs, or in that case, tilt wings in general. Okay, so with this, I'm at the end of this case study on tilt wing modeling and control. I hope you get some insights, and if there are any more questions, I'm happy to discuss them with you in the live Q&A. Thanks a lot for your attention.